Welcome guys, in this video we are going to solve the following LeetCode daily challenge. Maximum difference between node and ancestor. Given the root of a binary tree, find the maximum value v for which there exist different nodes a and b, where v is equal to absolute difference between a val and b val, and a is ancestor of b. And node a is ancestor of b if either any child of a is equal to b or any child of a is ancestor of b. Let's consider the following example. The maximum difference between two nodes in this tree is 13. We get 13 by subtracting minus 1 from 14 and we get 13. But this is not the correct output. This is not the solution to this challenge because these two nodes don't make any ancestor and child relationship. That's why this is not the correct solution to our challenge. We need to solve this solution. We need to find the difference between two nodes that makes ancestor and child relationship. The difference might be between these two nodes or these two nodes or any of these nodes that makes some relationship. And these two nodes, 1 and 14, don't make any ancestor and node relationship. To solve this problem, to solve this challenge, we need to traverse the tree, and while traversing, at each iteration we need to compare the current node with its ancestor or ancestors. Let's start traversing the tree. We go left. Okay, let's go left, and we need to compare this node with its ancestor, and let's write the value here. We need to compare its ancestor with this value. As we go deeper, we reach 1, and we need to compare 1 with 3 and 8. That's why I'm going to write these values that need to be compared right here. And then we go right, and 6 needs to be compared with 8 and 3. Actually, the minimum difference between the maximum difference that we get by comparing these values actually will be the result of this solution. And for example, by comparing these values, if we compare 8 and 1, the difference will be 7 actually. And this value is the result, is the solution to this challenge, because there's no any other relationship that is more than 7, and this is the result. But as you can see, while traversing, we are carrying some unnecessary values. For example, if we reach 4, we need to compare 4 with 4, 3, and 6. And right here as well, we need to compare 13 with all its ancestors. We need to carry all these values, 8, 10, 14. But actually, if we are carrying unnecessary values that don't make any sense because they are odd. Another efficient approach is the following. I'll show you in the next moments. Okay, let me delete all this stuff. While traversing, what really matters is to find to carry the maximum and minimum value while iterating. For example, if we reach 3, the maximum value will be 8 and the minimum value will be 3. And we go deeper. As soon as we reach 1, the maximum value will be 1. The maximum will be 8, and the minimum value will be 1. And as we go, we can go any deeper because the node 1 don't have any child nodes. That's why we need to go back in the result. Will be 7. We return this value to this node, And here we are going deeper, and on this iteration, when we reach 6, the maximum node value will be 8, and the minimum node will be 3. And we go deeper. Here nothing changes because 8 more than 7, and 3 is less than 7, because, and that's why the maximum and minimum values will be the same here, and the same as well here, because 3 is less than 4 and 8 is more than 4. And as soon as we reach the base case, the maximum difference will here will be 5, and will return 5 to this node. And when we return all these values from 3 to 8, the maximum difference between node and ancestor of the left subtree will be 7 actually. And this value actually the solution to this problem, because the maximum difference of right tree will be 2. Okay, let's solve. We go right, and here the maximum value will be 10, and the minimum will be 8. We go right, and the maximum value will be 14, and minimum value will be 8. Next, here the maximum value is still 14, and the minimum 8, because 8 is less than 13, and the difference between two nodes of the right subtree is 6. We return this value right here, and if we compare 6 with 7, the 7 was the difference between 8 and 1 of the left subtree, and the result is the max of both subtrees. We are comparing 6 with 7, and the result is 7. Well, let's go the solution and see. At each iteration, we need to track 3 values. This is the current node. To solve this problem, we need to track the current node, current max value, and min value. Actually, and when we read the base case, and when we reach this part, we need to subtract maximum minus minimum, and this is the result. Let's start writing the code. To solve this challenge, I'm going to use the recursive approach. Let's write the base case. When the root is null, I'm going to return the max value minus min value. Since the signature of this method doesn't include these variables, arguments, I'm going to add them. Okay, the max value will be of type int, and for the default value, it will have the default value of root value, and min value this. And next, all we need to do is just to recursively call this function for the left subtree and the right subtree of this root node. Max up ancestor div root left, and for the max value, I'm going to pass it the maximum value of both of current node value and current max value. And for the minimum value as well, the same thing. Current node value and minimum value from the argument. The same thing for the right subtree. Well, let's introduce local variables for both of them. This is left subtree, and this is for right subtree. sub3. Oh, there's a misspelling. Sub3 left. And the result will be the maximum of left and right sub3. Okay, this is it. Okay, let's copy and paste. I hope this works. Let's submit it. As you can see, our solution was accepted and the approach was pretty efficient as it beats 94% of users with Kotlin, and in terms of memory, it beats 86% of users with Kotlin. The time complexity of this algorithm will be O(n), and is the number of the nodes. And for the memory, for memory complexity, it will be O(n) overall. And n is the number of n is the height of a tree. Well, actually, if the tree is not balanced, it will be O(n), or in case so a tree is balanced, it will O(n) log n. Something in between. O(n) log n. And that's it for this challenge. I hope you really liked it. Please like and subscribe, and many more interesting yet to come in the future videos.